Infinite series. Here we have a sequence. It's an infinite sequence. If we took the terms of that sequence and we summed them all together, we would have what is called an infinite series. Now let's kind of compare these. So here was our sequence. Series and sequence are not interchangeable terms. The sequence is when we look at these successive terms here, and it goes to infinity in this case, and the series is when we sum up those terms. Now, notation for series, we use then the summation sign. We sum from 1 to infinity the terms of a sequence. So let's look at this series. And as we look at this series, we can see that the terms, if we put in 1, we'd get a half, plus we put in 2, we get a fourth, and so forth. As we look at this, it goes to infinity, but let's look geometrically here. Here I have a unit square. It measures 1 by 1, and I'm going to put the first term in here, which is 1/2 of that. So I'm going to shade 1/2. So the sum of the first term is 1/2. If I now add on 1/4, I'm going to shade half of what's left, which is 1/4, and the sum of the first two terms then is 3/4. Now I'm going to add on 1/8, which is 1/2 of what's left, and that would total 7/8. I can continue. I'm going to add on half of what's left, 1/16 here, and so forth. So the new sum is going to be adding these together plus this 1/2 to the n, and it's always going to be half of what's left as I do that each time. So you can see as I continue to do that and do half of what's left, half of what's left, half of what's left, half of what's left, that what I end up doing is filling in this square. So we can see this was a 1 by 1 square, that the total area that this covers is 1. So even though this is an infinite series, its total is 1. So we see that an infinite series can converge to a certain limit or value. In this case, it was a 1. We looked here at a sequence of partial sums as we were doing this, and anytime we sum up just some of the terms, we call that the partial sums, and we could write that like this. We're going to sum up n of those terms, and these partial sums form a new sequence, and it may or may not have a limit. The last one we looked at did, may or may not. Now we're going to define a convergent or divergent series then. So if this is the sequence of partial sums of this series, and S sub n denotes the partial sum, then S sub n is adding up n terms of this series. If S sub n is convergent and the limit as n approaches infinity of these partial sums is some value a, then the series we say is convergent, and we say the series equals a, so it's convergent to a. If the sequence of partial sums diverges, then we say that the series is a divergent series. Let's look at the geometric series. A geometric series is comprised of adding up the terms of a geometric sequence. And we remember a geometric sequence, we multiply each successive term by the common ratio r. So it could be expressed like this. We could write it as a summation. We got the first term and then the common ratio to the n minus 1. Now, does this series converge or diverge? Well, what if r was 1? Then if r was 1, each of these would be 1s, and we'd be adding up a plus a plus a n times. And as we let n go to infinity, this is going to go to infinity or negative infinity, depending on the sign of a. So it would diverge. However, if r was not 1, then we would have this sum, and we're going to take this and we're going to multiply both sides by r. So this would be r s to the n equal, this would be AR. I'm going to line it up over here. You'll see why in a minute. Multiplying this by r would be AR squared. Continue along, and we would have one here that would be AR to the n minus 1. When we multiply this last term by r, we would have AR to the n. Now I'm going to pull a little trick here, and I'm going to subtract these two. So I'm going to subtract this, and I'm going to subtract all of this. Now if I subtract this, I have s to the n minus rs to the n equals, now these will cancel, and all of these up to this will cancel, so we have the a on the front and then minus the a r sub n. Now I'm going to factor out the s sub n, so I'm going to have 1 minus r, then I'm going to put the s sub n here, equals, and I'm going to factor an a out here, 1 minus r to the n. Then last step here, I will divide both sides by 1 minus r. And what I now have is a formula for n terms of a geometric series. So if I'm summing up the different terms and I have n terms, I have a formula for this. So here it is. Now as we look at this formula, let's look at the r to the n, and what does r to the n do as n goes to infinity if this r is between -1 and 1. This is just simply r to the n is a geometric sequence, and we know as n goes to infinity, when we have our r between -1 and 1, that this is going to go to 0, because remember what we discovered when we looked at a geometric sequence. So that if we have the limit as n goes to infinity of both sides, that's going to go to 0, and we will be left with a over 1 minus r. So what we have here is the sum of a geometric series as n goes to infinity, as long as we meet this restriction here. R has to be between -1 and 1. So it will converge if the r is between -1 and 1, and it will converge to a, the first term, over 1 minus r, the common ratio. So here let's summarize that. The geometric series is convergent if the absolute value of r is less than 1, and the sum is a over 1 minus r. If the absolute value of r is greater than or equal to 1, we end up on the outsides here. The series is divergent. So notice this is the same as it was with the geometric sequence, except that with the geometric sequence we had this colored in because at 1 it converged to 1. But if you're summing up the terms in that sequence and it was 1, 1 plus 1 plus 1 plus 1 just keeps getting bigger, and so it will diverge if we're looking at the series. So it looks similar, but we do not include 1 for a convergent geometric series. Let's look at an example here then, and we see that we have this geometric series. We are summing these up, and as we look at the various terms in the sum, they appear to be approaching a limit, a specific value. In this case it looks like it's going to be 3. Well, we can look at that in a table and kind of see if that is the case, and it does appear to be narrowing in on 3. Well, we could look at a formula for this. It's the first term, and then the common ratio to the n minus 1 will give us the terms that we're summing for this series, and we now have this formula, and so we can compute this sum. That's going to equal the first term over 1 minus the common ratio. So when we add these together, we get 2/3 plus 3/3, which is 5/3. And so if we flip that over, 3/5, cancel the 5s, we see that indeed this does have a limit, and that limit is what we were seeing here, 3. Let's look at a different series, and one of the things we're going to do with this series is we are going to use partial fractions, and we're going to take this and we're going to split it up. When we do the partial fractions, we get a to be 1 and b to be -1. So this will split up like this. Now as we go to look at the terms that we're summing up for this series, if we put 1 in here, we see we get 1 minus 1/2. If we put a 2 in, we get 1/2 minus 1/3, and you can see the pattern that we have here. Now as we look at summing up the terms here so that we get this series from 1 to n, we can see that these halves would cancel, these thirds would cancel, and that would continue along, except we would still have this first term and this last term. So we could take the limit as n goes to infinity of the first term minus the last term, and as n goes to infinity, that's going to go to 0, and so we have this equaling 1. So this series converges, and it converges to 1. This is called a telescoping series, because think of the old-time telescopes here like Galileo used, and all of the middle stuff cancel and we're just left with the end. So it's like we collapsed it down and we are just left with the first part and the last part. So when we have a telescoping series, the middle stuff cancels and we've got the first part and the last part, and then we can see what happens as n goes to infinity of that, called the telescoping series. Now we're going to look at another series called the harmonic series. The harmonic series is just simply summing up the sequence 1 over n. So you can see what it looks like here, 1 plus half plus third and so forth. Now its name comes from the concept of overtones or harmonics in music, because the wavelengths of the overtones of a vibrating string are 1/2, 1/3, 1/4 of the string's fundamental wavelength. And so as we look at this, that's why we call it the harmonic series. Looking at that, if we sum these terms up, here's a sum of tons and tons of these terms, and it appears to be slowing down. It's increasing, but does it have a bound? It's not obvious in looking at this. If we looked at a table and we did in terms of this and we looked at the partial sums up to the nth partial sum, you can see as we get up here 10 to the 40th terms, we still appear to be getting larger and larger. So it possibly diverges, but we'll need a closer look at it. So let's look, and what if we added up the first two terms? We'd have 1 plus 1/2. So the s sub 2 is 1 plus 1/2. Now when we add on two more terms, 1/3 plus 1/4, that is 7/12, which is more than 1/2. So we could make the statement that the sum of the first four terms is going to be more than 1 plus the half here and a half here, because this is definitely greater than a half, so we know the sum is more than that. Now if we added on four more terms and we sum those up, that would be 533 over 840, which is also more than 1/2, because this number is larger than half of this. And so we would know that the sum of the first 8 terms has got to be more than 1 plus this half plus this half plus this half. We could continue with that idea, and if we added on and we got the next terms here up to 16, the sum of these terms again is more than a half. So the sum of the first 16 terms would be greater than 1 plus a half plus a half plus a half, or 1 plus 4/2. We could continue with this, and the sum of the first 32 terms would be greater than 1 plus 5/2, and of the first 64 terms would be greater than 1 plus 6/2, and in general the sum of the 2 to the n terms would be greater than 1 plus n over 2 then. And as we see that then, as we let n go to infinity, this is just going to go to infinity. So this is going to be getting larger as we go. It is not going to converge to a finite value. So the harmonic series is a divergent series. And as we look here, the terms themselves, we can see they're getting smaller and smaller and smaller, and the limit of the terms is 0. The terms are going to 0. We know if we took the 1/millionth term, we'd have 1 over 1/millionth, which is pretty close to 0. But when we looked at the sum here, it diverges. It does not approach a finite value.